various experiments, starting with palladium foils, trying to get extremely pure and things like that, we've discovered now that a few defects, in fact, may actually help the process. In this case, the defects were built in. So, you know, was it because of, you know, what was the cause? Was the deuterium built going in there cause the defect, or what? But in any event, again, these two things we now understand are extremely critical in the reproducibility of the experiment. Next. I talked about how fast it happened. Here's 60 minutes. Remember, it takes a couple of weeks before you would see a response from the Pons and Fleischmann approach. Using this approach, you know, we put a thermocouple right behind. In fact, actually, we epoxied it to the cathode. We had another one in the solution. We start the cell, and in a matter of an hour or less, the cathode would be several degrees C hotter than the solution. And that shouldn't be. You know, if it's joule heating, the solution should heat up. And there was a lot less resistance in the cathode than there was in the solution. And so this was our first clue that something was happening, and it was happening on the cathode. Another thing that Pons and Fleischmann talked about, they named it heat after death, is when you turn the experiment off, sometimes they saw a burst of heat. And sure enough, we saw the same thing. When we turned the experiment off, we would see a burst of heat and see it on our thermocouple. So, you know, we were seeing the same things that Pons and Fleischmann talked about, but in a much shorter time. And as I say, the electrode was warmer than the solution, and that shouldn't be. Mel Miles, who at the time was a scientist at China Lake Naval Laboratory, not too far from here, he did some co-deposition experiments, you know, looking at calorimetry, and he confirmed that the co-deposition reproducibly yields excess power compared to conventional palladium bulk cathodes, like it's starting with a wire or something like that. So, and in fact, Miles continues to this day. He was at China Lake at the time. He's now professor at Dixie State College, but he continues to work at this day and do some of the best calorimetry work that is being done in this field. And he has found that co-deposition not only is more reproducible, but it actually produces, on average, more heat than some of the other approaches, which is typically on the order of 30 to 40% excess heat. Okay, next. He also, you know, I mentioned some of the calorimetry that he's done, and also he's observed the positive feedback, which, you know, in talking to Fleischmann, he said when you get above about 50 degrees C, you tend to get more reactions and more events, and so we did some experiments along those lines, and Miles did the same thing and saw the same thing, the positive feedback. Okay. One of the ways we used the flexibility of the co-deposition approach was we took a nickel screen. We ourselves were literally little plastic boxes that you might buy at a jewelry or at a hobby shop. We cut a hole in it, put a Mylar window in it, mounted an IR camera outside of it, and then co-deposited onto the nickel screen and looked at the back side of it. And when we did that, what we saw here from the IR camera, and you can see the flashes, and over, you know, a very few seconds, you know, you'll see this what initially was just a few white spots expand to where it covers virtually the whole size of the electrode, and then you'll see the next color start to show up, and you know, at this point we're about up into here, but you'll see the next color starting to show up, and in a matter of a couple hours we can start down on this color, this temperature range, and move all the way up through here. And again, you know, the electrode was hotter than the solution. You can see the solution out here, the electrode, and again, this shows that a couple of things. Not only is the electrode what is providing the heat, you can see that the heat appears to be occurring in small, discrete bursts, and you can see here that the electrode surface is already expanded considerably as the temperature is heated up. Okay, one more time. Oh. Dave Nagel, who at the time was a scientist at the Naval Research Lab in Washington, he's now retired and an adjunct professor at GWU. He did some calculations to determine, is this chemical or is it nuclear? And by the way, when Pons and Fleischmann first made their announcement, they said, well, you know, we're seeing more heat here than we can account for by chemical means, therefore it must be nuclear. They really didn't have any direct evidence that it was nuclear, and you know, there's a statement, extraordinary claims require extraordinary evidence, and clearly they didn't have the extraordinary evidence that was required to make that claim. Well, Dave Nagel did some calculations and using all of these assumptions, the number of joules and everything, he concluded that the heat spots must be due to nuclear level energy releases. They could not be associated with a chemical release or chemical in nature. We showed this sequence. We had a meeting at our lab in about 2000, and actually I had invited, and Martin Fleischmann came to the meeting. I had people there from Lawrence Livermore lab, and we went through this, and one of the people from the lab, from Livermore, said, hey, you guys are in the Navy, you should hear these. If these are little mini explosions or something, discrete events, you should hear them. You're in the Navy, why don't you take a transducer, put it in the cell with you, and listen to it? Well, you know, hey, we're in the Navy, we can do one better than that. Using, again, the flexibility that the co-deposition allowed, we, next slide, took a transducer that had a silver face on it and co-deposited right onto the face of the transducer. And now, then what we could see is these kinds of spots where a pressure spike is down, and as you go, if you get a heat burst, then that causes the lattice to expand, and so that would cause it to come up. And you can see the types of events in calculating. We think what was happening is, you know, the pressure spike would come down very fast and impact, causing the downward spike, and then the heat expansion would come down and it would follow that, and so that's what would cause the rise in the signature. And so you can see, you know, we are getting these atypical, you know, down, up, and then kind of an exponential decay, which fits exactly what you would expect if you had a mini burst followed by temperature, and then it would decay back down exponentially. Next view, right. Other things that we did at this point and started to, we started looking for direct evidence of nuclear reactions and nuclear events, and certainly X-rays is one of those. Simple thing to do is take that piezo transducer that we had, or ferroelectric transducer. After we're done, take it out, dry it off, put it in next to some photographic film, let it sit for a couple of days, and then develop the film. And when we did that, we would see, you know, the shape of the electrode here. We've done this with other kinds of electrodes too, and you can even see, like in the case of a nickel screen, you can even see the screen, the pattern of the screen. We look for some gamma lines, and you can see significantly above background, and also some emissions over here. We've got the palladium K alpha line and the 8 to 12 K EV, either due to nickel or platinum that you see here. Next. Some more low intensity radiation, you know, and again, you can see, you know, the counts per second, or X-ray, and also gamma, and you can see that we're clearly above background, and so we're beginning to see, to address the issue of its nuclear, where's the nuclear ash, and so you can see that we're beginning to answer those questions. Next. Another thing that we did, there were reports that people were seeing tritium, and so we designed a cell co-deposition where we could collect both the gas and also look at the electrode and the solution, and you know, again, a good electrochemist took care of all of the equations. Next slide. And when they did that, we saw that we had of the 5 experiments, 3 of them gave a tritium rate of production of between 3,000 and 7,000 atoms per second over a 24-hour period. Now, we know they didn't occur in a uniform process. We would see spikes occur, but when we averaged it over 24 hours, 3,000 to 7,000 atoms per second were being produced. 2 experiments showed complete mass balance, so 2 of those did not produce tritium.